Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to introduce Juan Vera, who will be our speaker today. Juan is academically my twin brother. We've both just finished up working with Alan Friese at Carnegie Mellon, and now Juan's a postdoc working with Eric Vigoda at Georgia Tech. And today he's going to talk about Markov Chain Monte Carlo and randomly coloring planar graphs, which I think is a pretty exciting topic because, you know, this graph only needs 4 colors to be colored. So why do you need so many colors to randomly color it?
Okay. Thank you for inviting me to this wonderful place, especially to AV. So this is recent work that we have been doing the last months, and it was submitted to Fox, and was joint work with Tom and Hayes and Eric Vigoda in Georgia Tech. Well, Tom is in ITT. And this is my online, so I just skip the online and go to the, but I'll do an introduction, I'll show the results, some details of the proof, and some remarks at the end. And what we are interested is in uniform sampling of proper colorists of a graph G, so thinking a fixed graph. And why are we interested in such a thing? Because we want to run simulations. And from a more theoretical point of view, as color is in chart P, and we have this result by Jerome, Valiant, and Basirani, that we know that if we can give a uniform sampler for a set S, finite set S, then we can construct an F-plus for S, for compute the sizes of S. Having an algorithm that can sample colorings will give us an F-plus to compute the number of K colorings of a graph. And in a more theoretical, non-utilitarian way, the problem is challenging, it's interesting, and it's fun. At least for me, it's fun. So that's a reason to work in this problem. The way we're going to tackle the problem of sampling colorings is through Markov Chain Monte Carlo. And what we do is, Markov Chain Monte Carlo is an important and very useful tool to sampling from complex distribution. What you do is you define an ergodic Markov chain on the set from which you want to sample, such that such a chain has the steady-state distribution, the distribution that you want, the required distribution. You run the chain long enough, and then you get the current point that you have is your sample. And it has been used for volume computation and for estimation of the permanence of non-negative matrices. And it has been used a lot. These are what I consider the 2 most notable applications, at least theoretically. And so the Markov chain that we're going to use is what is called the Glauber dynamics. And this is the heat bath version. What you do in this chain is you start with some coloring, some proper coloring of the graph. And then what you do is you take a vertex at random, a random vertex of the graph. You choose a color C uniformly at random from all the available colors that you have for that vertex. And you recolor that vertex using that color. So in few words, you choose a random vertex, you want to recolor it, you choose a random color that it will maintain the property of the coloring. And what is known is there is this somehow natural threshold for Glauber dynamics. And it is the number of colors should be greater or equal than delta plus 2. Delta is the higher degree of the graph. And it is a natural threshold because Glauber dynamics is always ergodic when K is greater or equal than delta plus 2. And therefore, the unique stationary distribution is the uniform overall colorings. And there are graphs where Glauber dynamics is not going to be ergodic below this threshold, like the complete graph. And moreover, some graphs are not correlable below this threshold. So it's natural somehow that for general graphs, this should be a threshold. I will say some words later about this. And I want to go back to when I say how do we use the chain, the Monte Carlo, the Markov chain to sample. And I said in the second point, I said we run the chain long enough to get a close to the steady state. And the main question there is, what do I mean by long enough? How long is long enough? This takes us to the mixing time. So the mixing time is the time until the chain is, the distribution of the sample will be close to the steady state distribution. And I'm going to use variation distance. And the definition of variation distance, here is where I need the pointer. The definition of variation distance is this one. So this some distance between the distributions. Here, pi is the steady state distribution. And this one is the distribution of the t sample when I run the chain starting at x0. And what I want is this distance to be less than 1/4. And you can replace 1/4 bar by any of your favorite numbers. So you can get as close as you want, yes. Okay. And for Glauber dynamics, so I'm going to concentrate on the mixing time for Glauber dynamics. For Glauber dynamics, it should be intuitively clear that we need at least n log n steps, because that's the time that we need to at least see all the vertices. So that's not totally true. That's not the reason why it is true. But Hayes and Sinclair, they show that actually the mixing time is at least n log n steps.
You only showed it under bounded degree assumption.
Yeah, and the bounded degree assumption. Yes.
It's still open whether it's true in general.
Yes. Yeah. And there is this conjecture, that's kind of folklore conjecture, that is that in general graphs, the mixing time is going to be order n log n when k is greater or equal than delta plus 2. And what we are going to prove of the case that we are trying here is we're going to show that the mixing time is optimal, that meaning n log n, for the Glauber dynamics when k is smaller than delta. Yeah. This won't be true for the general case, for all the graphs. So we're gonna prove it for some large class of graphs, and that class of graphs will include the planar graphs. That, as Heidi said, if you need 4 colors to color a planar graph, why you will need k order delta to have a good sampling. And this is some history. So this is the history of the improvement that has been done towards the conjecture. So in 95, Jerun proved rapidly missing for k greater than 2 delta. And then Vigoda proved for 11 delta 6. And that's the best general result for general graphs so far. And then Dyer and Fries, they introduced the use of some properties of typical colorings. We will use also this. So, but they did it for some class of graphs, and basically what they use, that class of graphs have big GER order logarithm of delta, and also big delta. So they needed delta to be order log n. Yeah. And then the subsequent work was reducing this number, 1.763, or reducing the GER. So the GER was reduced like to 5, and then reducing the conditions on delta. So in this paper, they had a result where it says if GER is bigger than 5 and delta is some big constant, and alpha, this number is 1.5 something, then you have rapidly missing. You have missing time equal n log n. Yeah. On the other hand, Hayes and Vigoda, they gave a proof using non-Markovian coupling for the case where delta is still big, it's log n, GER is 10, but it works for k greater or equal, basically 1 plus epsilon delta. So that's sort of the state, the general state of the problem. And recently, Hayes gave a proof for planar graphs where k was delta plus of square root of delta. Yeah? And that's going to be our departure point. So Hayes proved this optimal missing time. When I say optimal missing time, I mean n log n, order n log n, for k equal delta plus little all of delta. Now, planar graphs are 4 colorable. So polynomial mixing time for k less than delta looks reasonable. And for example, the Glauber dynamics is ergodic for all k greater than 12. Yeah, so why should you have some big delta? Now, from the statistical physics point of view, yeah, if you consider the infinite delta minus 1 array tree, delta plus 2 is the threshold for the persistence of long-range interactions. That means if you fix the coloring of the leaves, somehow the root will be influenced. Yeah? In the threshold, I mean, if you go below the delta plus 2. So, in fact, there are some colorists where the leaves freeze the color of the root, meaning this is a natural threshold, not only because the chain is ergodic for all the graphs, it's because there are some more deep conditions there. Yeah? And it's actually, this is the kind of conditions that looks like is the natural reason for having those thresholds. And we're going to see that these frozen colorings is the major obstacle that we need to overcome to get rapidly missing. Yeah? And it makes sense. I mean, if colors are frozen and you're running Glauber, you will have to wait a lot until those vertices are actually changing colors to have an independent sample.
You're talking about trees here, right? I mean,
yes.
so, I mean, the other reason it's getting frozen is because you've got an extensive number of things that you're fixing that freeze it. So, is that relevant to other graphs? Do you know what I'm asking? I mean,
yeah, you mean you're
I mean, if I took Z2 or something, I took some planar graph, some some nice amenable planar graph.
You still have freezing.
You can
Yeah, you
still
still have-
have freezing
Yeah,
with.
I mean, if you take the tree and you map it down by.
And you found one of the
together.
frozen coloring
It's
and then
still-
edges.
Okay. Okay. Good.
Good question and good answer. Okay. So this is just to give us an idea, and I want to. This is an important point here, and is when we go below delta plus 2, we will have some frozen color, some frozen vertices. Yeah. So we had to overcome those frozen vertices. Yeah. Now, how below can we go? How much below delta can we go? Yeah. And we know that an easy conductance argument will show that the mixing time will be super polynomial in n when k is this order. Yeah. Now, what we are going to prove is that we can take k order delta log delta, that will be omega delta log delta, and we will have rapidly missing. Yeah. So results somehow suggest that the threshold should be delta over log delta. Yeah. But we haven't. We are still working in trying to improve the lower one. Okay. Now, what we are going to use, and
So you believe it's log and not some other sub,
yeah, no, we believe that is actually delta over log delta. Yeah, some constant delta log delta. Yeah, but that's the order.
obviously
Yeah,
constant,
yeah,
but I mean,
that's the order.
you-
Delta log delta.
'cause there's
Delta divided
room
by log
there
delta.
from log in to log
Yes,
delta,
yes, that's
right?
true.
You could imagine a lot of other functions in there.
Yes.
But you have reason to believe that
We are-
log
yes.
delta is the right function.
Yes.
Okay.
It's just that I think we haven't been able to get a good example where, but we have reason to believe that it's delta over log delta. And
Was there previously a better upper bound known for trees? Just the delta over log delta for trees?
instead of delta over log delta,
Yeah.
it was
no, instead of delta, or an upper bound.
Before your work, what was the best upper bound?
okay, it was delta plus little over delta by Hayes.
Even in the case of trees.
Even in the case of, well, no, actually for the complete trees case, there was some results of delta plus 2. But they were all sort of order delta.
Uh-huh.
Yeah. So, yeah, for trees it was order delta. And for planar graphs it was delta plus little over delta. And somehow it's natural. That you should think that it should be easy to go below delta. But somehow it looks that what the magic thing is the spectral radius. Yeah, so that's the magic.
Oh, actually, I think delta plus 3 is what Martinelli and Sinclair White's show. But trees.
Yeah, for trees.
Right. delta plus 3.
But is delta
With
measured
various
at the
boundary
root or at
conditions.
the, I mean,
No, it's not
a
because
binary tree has to
I
be 3 or
understand.
2, which?
in the same notation, and they comment on why it's one more than what one would guess.
So our result will be, what we are going to prove is, we are basically going to prove that we have optimal missing time for graphs of a spectral radius less than delta to the 1 minus epsilon. Yeah. So we're going to do the theorem. First, we're going to do an easy version of the theorem that it says if delta is still log n and k is delta over log delta, some constant that depends on epsilon, then the Glauber dynamics will have missing time, optimal missing time. Yeah. Now, for the general case, when we take out this condition, what we're going to have is if the spectral radius is smaller than delta to the 1 minus epsilon, delta is bigger than some constant that depends on epsilon, k is again delta, order delta over log delta, we will prove that the Glauber dynamics will have polynomial mixing time. Yeah. And we're going to prove that using some other dynamics that will have this mixing time, that is like n log square. Yeah. So we actually believe that the Glauber dynamics should have still the optimal missing time, but we weren't able to prove that. And our results apply to graphs with the spectral radius less than delta to the 1 minus epsilon. And examples of those graphs are planar graphs. They have a spectral radius order delta to the 1/2. And if a graph is embeddable, in general, graphs embeddable in any fixed surface of finite genus. So planar graphs is like the simpler case. Any graph such that the product of the degree of any two adjacent vertices is at most delta to the 2 minus 2 epsilon. That's because we have the spectral radius is less or equal than the square root of that product. Yeah? And in particular, bipartite graphs where one side of the bipartition has maximum degree delta to the 1 minus 2 epsilon. And unions of any fixed number of the above. Yeah? So we're trying to come up with interesting examples. So our interesting example was planar graphs, and then I think bipartite graphs is also an interesting example.
Missing something or normalization. I mean, for the expander graph.
So we have bounded.
You have an expander graph of bound. So your degree is not. Your degrees are really going to infinity for this statement.
No, really.
Can you show again the segment of the theorem?
The spectral radius of the lattice.
Yeah.
Not the
What is your spectrum of the adjacent?
The spectral radius is the maximum eigenvalue of the adjacency matrix.
Yeah, so it normalizes.
So it's at least the
Not
average.
normalized. So
okay.
It's least the average difference.
Otherwise,
So
Yeah, it's at least the average.
At least the average degree.
Yeah, and it's bounded by the maximum degree. Yeah, so in our case, it's at most delta. Okay. Yeah. Okay. Let's see. Okay, and the line of the proof is 2 lines. So first, we use the spectral radius to do a modification of Jaron's proof for the case k greater than 2 delta. That's basically the way all the proofs start. And then we use local properties of typical colorings. That is actually the way that almost all the proofs continue. So let's see some details of the proof.
5-minute Hamlet.
Yes.
Hamlet, there's some production. Hamlet in 5 minutes.
And well, this point is important to point out this here. When delta is this order, we have no frozen vertices. And then basically we will do like what is a standard technique now. You have no frozen vertices, and then you apply the standard technique. When delta is constant, then you will have frozen vertices, and what we had to do is to somehow work with them. Yeah, so. And what we're going to use is...
By frozen vertex, you mean a vertex where one step of Glauber dynamics cannot change it?
Yes, actually, I will mean something that is more like it has few available colors. But yeah, we can think in frozen vertices are those vertices where, yeah, one step of Glauber won't change it when you pick that vertex because you are watching all the colors. Yeah. So the point is we have a vertex could have delta neighbors, and you are using less than delta colors. So it could happen that the neighborhood of that vertex is using all the colors, except of course the color of that vertex. So when you pick that vertex to change the color, what you're going to happen is you're going to recolor the vertex using the same color that it had. So it is frozen. Yeah. And actually, when delta is constant, you could have chunks of frozen vertices, meaning huge. They will be connected pieces of frozen vertices. Yeah. So that's what we had to handle. Okay. So what we're going to do is we're going to use a coupling. So I wrote down a definition. And what we do is we create two copies of the chain at the same time, such that the marginals are the right marginals, meaning each marginal is a Glauber process. And then we're going to use the coupling theorem. And basically, it's here. What is written here is the important thing is if y0 is chosen uniformly or adversely, we will need t such that the expected number of disagreements, so this set is the set of disagreements, is less or equal than 1/4. That will imply that the mixing time is less or equal than t. Okay. So what we're going to do is we're going to bound the size of the disagreement set. Okay. So, and we are going to use Jarreau's coupling. And what you do, so remember, we are starting the chain with one color y0 and one color in x0. We're going to start running Glauber in each chain. And we want that after t steps, the two colorings are the same. That's basically what we want to do. So what we do is we choose the same vertex in both processes in every step. And then we're going to try to use the same color. That may be not possible. So we're going to work out the probabilities in such a way that we maximize the probability of choosing the same color. Yeah? So we couple the probability of which color we choose such a way that we maximize that probability of choosing the same color. And if you do the computations, then you get this lemma. And it's that actually the probability that you get a disagreement in the next step when you choose that vertex, meaning the probability that you are not able to choose the same color is this quantity. Yeah? And the bound that I'm going to use for that quantity, or that we are going to use, is this. The size of the number of neighborhoods of neighbors of V in the disagreement set divided by the number of available colors. I didn't say what this means, no? Well, these are the number of available, no, I said it. This is the number of available colors in each coloring. So the number of available colors in Y. Yeah. Okay? So that's the bound that I'm going to use for the probability. So this quantity is going to bound the probability that the vertex becomes a disagreement. Okay.
Can you go back to the
Yep.
first? These are the available.
So
It's a function of x.
I think you're right. It should be 1 minus that.
Yes.
Yeah. Okay. Yeah. Yeah. It's 1 minus that. But the bound is okay. Yes. Because because we are using the probability that it becomes a disagreement. Yeah. But the second bound is right. Is the number of.
I was focusing on the first one and it wasn't working. Okay. The second. So what do you have in the second one? Yeah.
So the second one. Yeah. Okay. So this is the bound that we're going to use. And then somehow I had to use the spectral radius. So to do that, I introduce weights. So I'm going to introduce a vector of positive weights. And then given two colorings, xt, yt, and v, I want to compute what is the expected increase in the weight of the disagreements, given that I choose t and I have xt and yt. Yeah? So that is equal to, I choose v. Yeah? So this part, we should think like when you choose v, If it was a disagreement, you are taking it out of that set. And then what is the probability that V becomes a disagreement? And that's the bound that we just wrote in the previous slide. So we get this quantity. Now, if I add over all the possible V's, and I put this 1 over n because I have the probability.
Oh, so now you choose V with probability proportional to W?
No, here I'm conditioning on choosing V. I'm not changing the chain. Yeah?
Oh, I see.
Okay? Okay, it's just the metric. So I'm using a weighted metric. Yeah? So the weight will change of the weight of V. The change in the weight will be the weight of V. And this is the probability that that weight is going to change. And so if I add over all these, I will have this equation. Okay? So what it says is add over all these here, and the probability that you choose each B is 1 over n, so you get this. Okay? Now I do a change of, I write this size of mv inter dt. Well, I do a change of summation here. I do some algebra there. Yeah? And then I get this expression. So we get that expression, and let me make emphasis in the interpretation of this expression.
Less than.
Yeah, less that. Thank you. This is a less that, and this term comes from when we choose a vertex. We first take it out from the disagreement, and this term is the probability that a disagreement will propagate. So if I have a view in the disagreement, the probability that it will propagate to a neighbor will be 1 over the available in that neighbor. Okay? So.
But you can also choose a vertex that wasn't in a disagreement, right?
Yes.
And then a disagreement can be created.
Yeah, but here what I'm choosing, the vertex that I've been choosing is B. So I'm not choosing U. So what is the probability? So what I'm trying to say here is, what is the probability that a disagreement propagates? Let me do a plot. Actually, this is a comment. This is a talk about coloring graphs, planar graphs. So it should be full of plots everywhere, but it has not plots because I couldn't make up my mind where was a good plot to put. So this is the graph. These are the disagreement sets, let's say. This is the disagreement set. What is the probability that a disagreement will propagate? For that, I have to choose a vertex that is in a neighbor of a disagreement. Yeah? And the probability that a disagreement will propagate from this vertex to this vertex is this 1 over availables of this vertex. So this is V and this is U. The vertex that I'm choosing is V.
Okay.
Okay? That answers your question?
So it is a good vertex turning into a bad vertex.
Yeah.
It's the only ones that could are the ones
Okay.
that are neighbors of the bad ones.
Yeah. Okay, so we get that equation. Now I keep doing some algebra in it. So let's assume for 1 sec that we have a bound like this. The number of available colors for a given vertex is greater or equal than something that I call A mean. Yes, for every time t and for every vertex v. So I'm gonna just take this term out here, bounded by 1 over A mean. Okay, and now if I take W to be the corresponding eigenvector for rho, I get this expression. Okay, so what I get is this inner sum here is just less or equal than rho W of U. I take rho out and I get the sum of the W of U's. I get W dt.
You're really going to have a uniform lower bound, uniform in V?
No.
Okay, so it's this.
Assume
plus
we
the
have
plus
that,
one.
yeah, and then,
Fine, 'cause
yeah.
It's not, yeah, okay.
Ouch. What did I do here? Yeah, like if delta is big enough, then we will have a uniform lower bound with high probability, and we have this
Right,
error
then you have
term.
to let-
Yes. Okay. So summing up what we wrote there, so the expected change will be something like this. Yeah. So we had this. So that's the equation that we got. So if rho is less than this bound that we have, then we get optimal missing time. Okay? And then, in particular, a bound that will always work will be k minus delta, and that will give us the Alger runs. So the Jeroen's proof is basically the case where rho is delta, and then we get here k greater than 2 delta. Okay? And if we use the rho is delta to the 1/2 for order delta to the 1/2 for planar graphs, we get the result for planar graphs. Yeah? And that's basically the proof for planar graphs. Okay? So now, how do we get below delta? Yeah, that's the question. So it looks here, just using the spectral radius won't take us below delta because we have k is greater than delta plus rho. Yeah, so we have to do something else. And what we're going to do is we're going to use properties of typical colorings. So the point is, if I take a typical coloring, I take a uniform coloring of the vertices, how does it look like? Or especially, what is the number of available colors that a vertex will have? Yeah, that's the question. And the point is, if the colors were taken independently at random in the neighbor, yeah, then the number of available colors will be this binomial variable. So this is the probability that I haven't used the color in each of the delta vertices that I see in the neighbors, and this is, and then I do it for each color. So if you do the math, the algebra, if k is bigger than this delta over log delta, then the number of, a lower bound for this will be something of this sort. And here I mean by with high probability. Okay? And therefore, rho, if rho is less or equal than delta to the 1 minus epsilon, we get the rho is less than this, the rho over divided by mean is less than this quantity, and we get optimal missing time. Okay? So that's the whole idea. Now, but here I was assuming that the colors, the vertices were coloring independently in the neighbors, and we know that that's not the case. So we had to go through those details, and the main lemma will be, I'll do this version first. When delta is big, it's like log n, and k is this order, then if I choose a uniform coloring, the number of available colors, the probability that I have a few available colors is less than n to the minus 4. Okay? And then, as Jennifer said before, then you condition on this, and you do the expectations, and you work out the expectation, and you get the optimal missing time. Okay? Now, how do you do this? So the key point is, I want to prove that if I choose a...
But when you define the mixing time, you start with the worst vertex, right?
I start with the worst coloring. Yeah, but that's x. X is the worst one. But y, I had the freedom to choose it uniformly, or to choose in also worst case.
I see. So it's enough that one is okay.
Yeah, y could be chosen uniformly, and that's something that we're going to use. Okay. So that's why I was using all the time in this bound.
So it's enough to
have the bound. That's why I bounded here. Here there was the maximum between the availables in y and x. That's why I replaced it by just this one. Yeah, because I know that I have the freedom. Yeah. Okay. So we want to prove this lemma. And the key point proving this lemma is, if y is chosen uniformly, and I pick a vertex, now if I recolor the elements of the neighborhood, yeah, so I condition on all on the colorings that on all the colors of all the vertices that are not in the neighbor, yeah, of V, and if I recolor those elements as in Glauber, then the coloring that I obtain is again uniform. Yeah. Okay, so that was a good point for a picture also. Because he's starting in a uniform one.
If I was trying to say that about something other than uniform, that's absolutely not true.
But it's because we are basically doing Glauber.
Stationarity of the uniform, yeah, but that's exactly what
Okay.
I was just thinking arbitrary y, not true, but it's uniform is stationary.
Okay. So that's the key point in many of the proofs of, for proving, for bounding the available number of available colors for uniform colorists. Now the main problem here is that NB could be already frozen. Yeah. So if the neighborhood of V is frozen and I try to recolor it, I will get that V still has the same number of available colors that at the beginning. So I'm not gaining anything. Okay. So what we are going to do, and so we could have some frozen vertices here because we just want a bound of this type. So we can have this. We can even have more than this, but we're going to use that we have the most frozen vertices on neighborhood of V if we do the things carefully. Yeah. And by carefully is, what we're going to do is we use the spectral radius. So the spectral radius was used in the algebra before, but here it will be a key point. So we're going to use the spectral radius to get that our graph has a tree-like structure. Yeah. So we're going to partition G. We're going to partition G in levels, yeah, such that each vertex has all but delta to the 1 minus epsilon neighbors in the previous levels. Yeah. That means the tree-like structure I mean here is each vertex has like delta to the 1 minus epsilon parents. So thinking the complete tree. Yeah. Mm-hmm. So if you want to recolor the complete tree in such a way that you don't get frozen vertices, what you're going to do is you recolor first the leaves, because the leaves are not frozen, and then you recolor the next level, and then you recolor the next level, and you keep going in that way, and you won't get frozen vertices, at least for this range of delta that we are using. And here we just basically do the same. Yeah. So we do the recoloring level by level, yeah, and we prove that in each level we don't get any frozen vertices. And then we do it as using a summa. So we first do the expected value, and then we use a summa.
If you didn't have rho less than delta to the 1 minus epsilon, you wouldn't have this hierarchical structure that you could start from the leaves and work in.
So it is an interesting question in the case of delta regular trees, delta regular graphs. Yeah, those graphs, in those graphs, rho is equal to delta. Yeah, and it's an interesting question. Can we go even below delta thirds? So just or delta halves. If I gave you k equal delta halves, could you have rapidly missing time? Could you have even proving this uniformity property is not known. I mean, if you can get this uniform property. So that's so here the rho here is very important that we have this condition. Okay. So now for delta constant, I will do more hand waving. It's more technical, but basically we couldn't do it for Glauber, and the problem is, let's say you start even with a complete tree, and you have only one disagreement here, yeah, but your tree is frozen. Yeah, so how is the dynamics going to behave there? What is going to happen? Well, your tree will be frozen like up to here because these are never frozen because these are leaves. Yes. You will have to wait until the non-frozenness start propagating up. Yeah. But while you wait for that, or not frozen, almost frozen. So these guys have some available colors, but only like 2 available colors. So what is going to happen is that the disagreement is going to start propagating down, while this non-frozenness is going to start propagating up. And then there will be some frozen chunks here, so the disagreements, if the disagreements are right there, they will just propagate, keep propagating, and then we don't know exactly what is going to happen there. Yeah? So even for the complete tree is quite difficult to know exactly what is going to happen there.
The question is what I mean, we do know that on the complete tree, even with 3 colors, it's always polynomial.
Yeah, but I mean, like, I was thinking like in our way of thinking. Yeah, like we do in this way that we are thinking, yeah, trying to get uniform properties, yeah, we are not going to get it. Yeah. So even exploiting this structure. Yeah. So And what is the problem? The problem is that disagreements are propagated, and we have to wait too much to get the non-frozenness going up. So what we do is we say, let's do a new dynamics. In this dynamics, what we're going to do is first these levels in this order. In that way, disagreements won't propagate down that much, and the non-frozenness will propagate faster. Yeah? And so what we do is we call it the level set dynamics. And basically what we are trying to do is to emulate the idea of the previous proof. We divide the graph in levels, and we run Glauber in each level long enough. And then our proof of uniformity will still work. Yeah? And it's much more complicated, but it still works. And we use, again, compute expectation, do a summas, and it's basically the same proof. And the point is that the probability of being frozen, if I give you a vertex in a level, the probability of being frozen will be of this order. Yeah? And then the weight of the disagreements will be still decreasing. I will say some words in the next slide about this. And the point is that the missing type of Glauber dynamics will be bounded. That will follow from doing a Markov chain comparison argument. Yeah? So as we are able to bound the missing time for this chain, we can get a missing time order of a star of M4. So that was our way to solve the problem. And so I'm going to explain a little the details of how the weight of disagreements are still decreasing, because those equations that I showed at the beginning will still kind of hold, but they don't really hold. And then what we do is, because of linearity expectation, we have to consider each disagreement separately. So here we are not doing path coupling. For some technical reasons, we cannot do path coupling. But it's like doing path coupling, but instead of doing each disagreement separately, we do all at the same time. So that's linearity of expectations. So we say, let's take a disagreement, let's see how it propagates. Yeah? So it's like kind of path coupling, but it's not path coupling argument. And our lemma is that the expected weight of the disagreements, if the disagreement is in a given level or at the neighborhood of a given level, then the expected weight of propagation will be this. So it is decreasing by this factor. That is basically the same factor that we had before. And to do this, what we do is we take a ball around the vertex, and we say, okay, the bad events are that actually here is not all, here is some vertex. So our first bad event is that some vertex is frozen, and our second bad event is that a disagreement escaped from the ball. Okay? And then what we do is we show, from the union bound you get that the probability that some vertex is frozen is this quantity. Yeah? Now if I tell you that it's non-frozen vertex, so V means there is no frozen vertex in the ball. So now we are like in the previous case. Yeah? If there is no frozen vertex, the probability that it will escape is this quantity that we can bound by this. Yeah? So this is a path of disagreements argument. And then we had to compute how is the way going to behave when the good events happened, and it will behave like this. Yeah? And then we had to find a bound when these two events happened, and that's this M here, and we use some rough bound there since work because these probabilities are really small. Okay, so that's the idea of the proof. So that's it. So concluding remarks, what we did, we studied Markov chains for coloring graphs with maximum degree delta. We want to do K colorings. And we give here, this is not true. These are not the first result, but these are first result for general class of graphs. And it depends of how general, what do you mean by general? You know, like trees or, but, well, I don't know. I just copy it from the paper. So And and the
Mark wrote that part.
and the challenging part, the challenging aspect of the worry is that when k is less than delta, even in a random coloring, a constant fraction of the vertices are frozen, and somehow you have to deal with that. Yeah. And well, our results hold for a graph with a spectral radius that is bounded, and it's not only because of those equations where it nicely interplaced there, but it's because of the structure of the graph that permit us to say something about the uniform colorings. Yes.
Can you say, you didn't say anything about how you get the levels, how you use a spectral radius to construct this tree structure. Can you say something about that?
Okay, yeah. There are two. Actually, you can just define it. Like the first level is those vertices that had bound degree less than this value. And then you erase those vertices, and the next level are those vertices that are now have that radius. Yeah. And then what you use is that the spectral radius is closely related to the average degree. So having spectral radius delta to the 1 minus epsilon give you average degree delta to the 1 minus epsilon half, something like that. And then that will give you that you should have
so
such
vertices. All you need is average degree in this dilemma.
In the construction of the structure you need it's like local average degree. It should say it's not just average degree in the graph, but it's also that any subgraph, that the graph that is left, what is left will have still this average degree property. Yeah, so it's yeah. So that's where the spectrum. There is other way also to construct it, and is you say I take the eigenvalue, the eigenvector corresponding to this eigenvalue, and now I will order the vertex according to the weights. Yeah, and now if you take levels. I mean, the weights will give you the levels. So somehow, what I mean by this is, if I have the number of vertices in the neighbors such that the weight of U is greater than the weight of V, this is going to be less than delta to the. This is less than rho. Yeah. So you can say. Let's assume the minimum weight is 1, and now all those vertices that have weight between 1 and rho, I will call the first level. Between rho and rho squared is the second level, and that will give you a gain. Yeah. So it depends on what kind of structure are you more interested. And there are some technical details that we have to play a little with the weights to. Yeah, but I didn't want to. Okay. Is there any other question? Yes?
So I guess more on Hayes' work. What was Hayes' idea in the delta plus root delta?
He used the spectral radius. Yeah. So basically the proof that I did here is basically Hayes' proof. He does it in a different way, but it's basically the same. So he used the spectral radius, and he basically used this property. If this is the adjacency matrix, then this is rho W. Because of the definition. Yeah. So, and that's the property that we are using in those sums. Yeah, but he used the spectral radius. Yeah. That's what hints us to work with the spectral radius. And then.
So for balanced finite regular tree in delta, but there I'm sure that the delta over log delta should be the right order. Right, but what lower bounds are known?
So far we know. Is there any way to go faster here? Well, the delta over log n that I mentioned is the only that is. Yeah. So there's a big gap there, but it should be delta over log delta.
For the Ising model,
yes,
we know some more, and what happens there suggests also.
Okay.
Yes.
What was polynomial for three colors?
So the mixing times, polynomials in the volume. I mean, any fixed ergodic chain on trees, the mixing time is polynomial.
So, but this is specific for trees. So.
That's specific for trees.
Right.
Sorry.
But not, it's in Glauber? Not Glauber.
This is Glauber.
Where's Glauber?
Right, so it's that's when.
Okay, so polynomial versus n log n.
Right.
Yeah, that's the. Okay.
That's actually what the part was added when Noam was
Right.
joined that paper.
Yes. This is for trees with fixed.
No.
So the degree is constant, or could it be a function of n?
This is right. This is for
Has to be
for
constant.
constant degree. Right, so when the degree is constant, the level is increasing. And it's polynomial, but the degree of the polynomial could
Depend on the degree.
Okay, thank you.